Okay, so in this lecture, we will be starting the topic gears. What we know is that gears are pushed elements making around the profiles of one another. Okay? The profile of one tooth of a gear mates with the profile of another tooth of the other gear, okay? The machine gear. And the contact is through higher pairs line contact to transmit power. Now, there are quite a few basic terms and definitions terminology in gears. Most important is the pitch circle and pitch radius. So, the circle over which you have the mating gears effectively roll. That is, if you replace the meshing gears by friction discs so that they touch each other and the motion transmission is equivalent to what the gear gears transmit to one another. Okay, I mean one of the gears transmits to the other. So that same motion can be obtained by a pair of friction wheels. So on which on one of those friction wheels, the other apparently rolls. There is a common pair. So that corresponding circle is called the pitch circle, and the point of contact is pitch point. So kinematically equivalent to a pair of friction discs. Now the radius of that circle is the pitch circle and diameter is the pitch diameter. And the point of contact of the two pitch circles is called the pitch point. Okay. Now, based on the size and the number of teeth of the gear, there are a few definitions. In fact, one is independent, others are related to that. So the circular pitch. Pi dt, that is circumference, divided by the number of teeth, n. So this is called the circular pitch. So the entire length of the circumference divided by the number of teeth. That means the part of the circumference that is crossed over in through engagement of one tooth. Okay? So it is the distance covered between corresponding locations of the two consecutive teeth along the circumference. Okay? So, and if you get rid of this pi, then that is called module, and the reciprocal of the module is the diametral pitch. Okay? So the circular pitch and module are in length units, millimeters kind of thing. Diametral pitch is basically the number of teeth per unit diameter. This is a very awkward term, but it is called. Okay? Now, from the geometry of the gear, there are a few more things here. That is this top of the tooth, there is a flat area that is called the top line. Okay? And the circle matching all the top lines together is, I mean, it's not exactly flat, but it could be almost flat for the smaller distance. So all of these combined together, this circle is known as the addendum circle, and the radius of that beyond the pitch circle radius is the addendum. That is beyond the pitch circle, whatever extra you have to go radially outward, that quantity is called the addendum. Similarly, rather than adding, if you deduct, then you get here the bottom line, and from the pitch circle, as much radially inward you need to come, that is called the dedendum, and this circle is the dedendum circle. Okay? Now, dedendum is typically higher than addendum. We'll see why. And the difference is known as clearance. And that makes sense when the meshing tooth, the mating tooth comes inside, then between the dedendum circle of the other one and the addendum circle of this one, that much is the clearance. There is the difference between dedendum and addendum is the clearance. And that is necessary because if these clearance were not there, then the top line of the other tooth of the other gear would interfere with this. Okay. Fine. So these are the basic definitions that you have to typically get home with. To continue. Now, since a pair of gears is basically to transmit motion from one shaft to the other. One of the gears is mounted on one shaft, the other gear is mounted on the other shaft. And to the two, motion from the driver is transmitted to the driver. So, we will be typically interested in the speed ratio, omega 2 to omega 1. Between two gears, the module has to be same, otherwise the machine will not be appropriate. And on the first gear, having angular velocity omega 1, there are N1T, and on the second gear, with angular velocity omega 2, there are N2T. Now, one tooth of this mates with the other tooth, one tooth of the other pushes it, then next tooth of this and the next tooth of that comes into play, comes into engagement, and so on. So one tooth and one tooth of the two gears typically engage together. I mean, together there can be more teeth of this engaging with more teeth of this, but as one tooth of one gear passes through the zone of engagement, from the other gear also exactly one tooth would pass. Okay? Because it is a direct transfer of motion to pushing. So if you consider such N1 into N2 tooth-tooth interactions, then during the passage of these many tooth, basically every tooth in several cycles would pass through several times to the common engagement zone. So the gear with N1T would make N2 rotations through these many tooth-tooth interactions, and the gear with N2T would make N1 rotations. Now, so omega in the same time this happens. So while the first one makes N2 rotations, the second one makes N1 rotations. And that would give you the speed ratio directly. So omega 2 by omega 1 is minus N1 by N2. Because the first one makes N2 rotations and the second one makes N1 rotations. Minus because the sense of the rotation would be opposite. Okay. And since module is same, so R1 by N1 is equal to R2 by N2. Okay. So R1 by R2 is the same as N1 by N2. So this and this are equal, where the R1 and R2 are the fixed circles. Now, without special measure, this constant value would be only an average speed ratio. The average speed ratio will remain constant without any special measure. In that case, without any special measure, what would happen? That over a cycle, while you will find this to remain alright, but during the cycle, there will be fluctuations. Okay? If the teeth engagement are without any special geometric profile. Now, for constant instantaneous speed ratio, for this value to stay constant over the cycle, the profiles of the teeth, profile of this tooth and the other tooth, okay, teeth of this gear and the teeth of the other tooth, have to satisfy the so-called fundamental law of gearing. What is that? The fundamental law of gearing says the common normal of the two profiles at the point of contact must meet the line joining the centers of the two gears at a fixed point. Okay. Through the teeth passing through the engagement zone, the common normal at the point of contact should not change its point of intersection with the center to center line. Okay. So it should meet the line always at the same point on the center. Okay. The fixed pitch point. The pitch point should be fixed. Okay. And at that pitch, of course, pitch point is fixed because it is the common point of alignment of the two pitch circles. But the common normal to the two profiles should pass through that point all the time. So this is the fundamental law of behavior. This condition needs to be satisfied for the fluctuation of this to be zero. Okay. Cyclic fluctuation of that to be zero. And for that, you thought of conjugate profiles. Given a curve as the profile of a tooth of one gear, you can work out the profile of a tooth of the other gear so that the two together satisfy this common normal condition. Okay? This fundamental law of behavior. And then these two will be conjugate to each other. These two profiles will be conjugate to each other, and they will together produce a conjugate action. Okay? And the interesting thing is that the conjugate profile of an involute profile is also an involute profile. So this is the reason. I mean, if you take some other curve as the profile of one of the gears, then there will be a different type of curve, a different type of curve which would match for the, which would make proper profile for the other two of the other gear. So for involute, it happens that its conjugate is also involute. So that makes involute the involute profile as the preferred profile of gear 2. Now what is an involute? The locus of a point, here there is something missing. The locus of a point, let me just write it here. On a line. The locus of a point on a line rolling over a circle. You have a hold a circle and then take a line and roll it over the circle. Then as you do that, the locus of a point on the line will describe the curve that is the involute. Alternatively, you can take it like this. I mean equivalent. You take a cylinder and turn a thread along it, okay, over the cylinder, and hold it tightly at one end, and then pull that, keeping it tight, keeping it taut, pull it. So as you pull it, so and pull it and like this, keep on pulling. Then a point on the say this circle, you hold the string like this and start pulling this way. Okay. So starting from A, the point comes like this on this straight line as you keep it tight. But then at the same time, this circle is going to rotate. Okay. So in the frame of reference of the circle, as fixed on the circle, the point A would go over a curve, and that is an involute. So a point on a taut string being unwound from a circular cylinder. Good. Okay. Around the axis of the cylinder, you do not consider any variation. So that is an involute. Now for involute profiles, tooth motion transmission is equivalent to the crossroad drive, where pulleys of radii is RB1 and RB2. Okay, RP1 and RP2 are the pitch radii, and if you consider base circles RB1 and RB2, which are given like this at this angle alpha between this point and this point. Now, these two bigger circles are the two pitched circles, okay, RP1 and RP2. Okay. And now, like this, you draw the line, okay, so this P, which one, point of contact of the two circles. And then this is RB2, this is RB1. Now, whatever the transmission, motion transmission would be there between the two gears, it would be kinematically same if you rather have a smaller wheel here and a smaller wheel here compared to the pitch circles. And then you have a rope drive, a rope, then cross rope like this. It will be the same transmission rather than the gear here. And from here you see that relative to this wheel, the point on the rope could essentially execute, will essentially traverse over an invalid. Similarly, on this also it would be an invalid. So the two invalid profiles, this, then top line, this, the top line. And point of contact, at the point of contact, the common normal passes through this point. So this is the kinematic equivalent. And that obviously gives you an invalid according to this definition of the invalid. Right? Now a few other things which you should know in general about standardization. Addendum is the same as the module. Dedendum is quarter times higher than the module. And the pressure angle is typically kept 20 degree or 22.5 degree and 25 degree. Now, these are standards set so that for different purposes, you have gears which do not have a continuous distribution of these properties, but certain preferred values. Okay? So that you do not have difficulty in finding matching machine gears. Now there is one more thing called interference. That's an issue. See, the involute profile does not exist inside the so-called base circle or the equivalent pulley in the cross rope transmission system. Okay. So it starts from that circle itself, outside the base. So inside does not exist. So inside the base circle, the profile is assumed to be continued as just radial. Because at the base circle point, the involute profile happens to be radial. So it is just continued in that radial direction. However, the involute profile of the mating tooth of the other gear may continue further because for that it is outside. Okay. So if its addendum is large enough, okay. So the involute profile of the other one might interfere with the radial profile of this one if it is not tangential. In general, it will not be tangential. So one remedy is to cut it during the radial portion, cut it a little deeper so that the extra depth of the other one entering into this has enough clearance, okay, rather than hitting with the radial profile. So that is called undercutting. However, if you undercut the tooth, then there will be a concavity made there, and the tooth, the undercut tooth, would be would become weaker. Its strength would suffer. And the only way to avoid this interference without this undercutting and loss of strength is if the addendum circle of the machine gear remains within the line segment of tendency, that AB. If within this point to this point, within this line segment, the addendum circle of the machine gear remains, it does not go beyond A on this side or beyond B on this side in the common tangent, then undercutting will be avoided even without, interference will be avoided even without undercutting. So that is a condition. And for that to be ensured, you can just do a simulation and find out that it happens like this. Otherwise, we need to undercut. And it has a relationship with the pressure angle, which is this alpha. Okay. So this much on the basics of gears, and in the next lecture we will study different kinds of gears and gear trains.